All right, so welcome back to 8701. So we have all ingredients now to prepare Feynman rules for QED. So that's the toolkit we need in order to make calculations, to calculate scattering processes and decays. And we have already seen Feynman rules for our toy theory. Again, now the situation is a little bit more complicated because we can consider the spin of particles in addition to their energy and momentum. The rules sequence of things are very much the same. There is, however, a few caveats to keep in mind, and I'll point those out. Okay, so the very first thing is to be very clear in our notation. So this is an arbitrary or generic QED Feynman diagram. We are only pointed out the incoming and the outgoing lines. So there is internal lines, which I didn't mention here. Important to note the momentum, and the directions. The directions are arbitrary. We just have to be clear on them and then treat them consistently. All right, so this is not different in our previous discussion. Then here comes the difference. Our external lines are either electron, positrons, or photons. Right, you can fermions and photons, charged fermions and photons. So we discussed how those solutions look like, our spinors U and V, and for outgoing electrons, for outgoing particles, we have this adjunct vector here, which is given by U dagger gamma 0. And similarly for the incoming antiparticle, V dagger gamma 0. For the photon, we have the polarization vectors for incoming and outgoing photons. All right, then we have a vertex factor. Here now G0 or GE is a constant and a dimensionless property. But we do have to have a gamma mu here as part of our vertex factor. For the propagator, our internal lines, we have a difference between electrons, positrons, and photons, and that comes from the fact that electrons and positrons are massive particles. So we have vertex factors which have this 1 over q square behavior, or 1 over q square minus m square behavior. So here you can already see that there's going to be a complication later when we evaluate or integrate our momentum. Simply the same discussion I had before, and we already know how to solve this problem of infinities by renormalizing, by having a cutoff and renormalizing. Excellent. So the next step then is very much the same. There's no change. We have to make sure that there's energy and momentum conservation, and we enforce this by introducing delta functions. We have to integrate over each and every internal momenta, and each internal line gets one of those integration factors. And then after we integrate, we are left with a delta function, and we have to cancel that delta function. All right. In our toy experiment, the order of things didn't matter. Everything we had in there was scalars, numbers, right? Here, we do have a little bit more complicated problem. So there's an importance in the order of which we execute things. So what we want to do is, form fermion lines. We just follow a fermion as we go from the left to the right, and you will find things which are always of the form an adjoint spinor, a 4 times 4 matrix, and a spinor. And the result of this is going to be a number. All right, great. There's one additional complication, is accounting for duplications and making sure that the sign is in. And I'm just mentioning this here. This will become more clear as we walk through examples. So there is an anti-symmetration going on, where we have to introduce a minus sign between the diagrams, between different diagrams that differ only by the interchange or the exchange of 2 incoming or 2 outgoing electrons or positrons, and or the incoming electron with an outgoing positron. So if you have a diagram which is exactly the same, but the 2 incoming electrons are interchanged, you have to add those 2 diagrams. You have to add all matrix elements together before we calculate an amplitude. But you have to introduce a minus sign when you change those 2 particles. So with that, we can now just basically calculate whatever QED process we want. All the tools are already here. And what we want to do now next, in the next video, also in the recitation and homework, is to go through a few examples to get a little practice with this. There's a number of tricks which will become handy, and I'll explain those in a separate video. They're just mathematical tricks which allow us to quickly evaluate the multiplication of spinors and matrix elements and so on. All right, that's it for this video. Again, there is going to be another 2 or 3 videos which deal with actually evaluating or calculating matrix elements.